Okay, so this is section 8.2, integration by parts. And in our introductory page here, the textbook gives us a simple proof as to where the integration by parts formula comes from. We're going to be using this formula to find the answers to our antiderivatives. And if we look here, this is an example of the product rule. We see that we have a function u and a function v. They are both functions of x. And when we use the product rule, it is the first function times the derivative of the second. That's what we have here. Add to that the second function times the derivative of the first. That's what we have here. And they're using the dv dx notation and du dx notation at first, but notice they switch it to v prime and u prime. Now, from here, they're going to say, well, the inverse operation of derivatives is integrals. So if we take the integral of both sides of this equation, we see that the derivative and the integral cancel each other out here, and we're left with just a u times v. And then we have the integral of u v prime, and they put the dx here because we're talking about functions of x, and then the vu prime in the next integral. And if we rearrange this a little bit, if we subtract, you'll notice they subtracted the v du. So the v du is being subtracted from the other side. You're left with, I'm going to subtract this from the left-hand side of the equation. You're left with what you see down below here. This is the formula. So the derivative by product rule is then integrated and rearranged, and that's how we get this formula here, and we're going to apply this formula. Now, the book gives us some guidelines for integration by parts. The first guideline it says is, try letting dv be the most complicated portion of the integrand that fits a basic integration rule, then u will be the remaining factors of the integrand. Their second suggestion is, try letting u be the portion of the integrand whose derivative is a function simpler than u, then dv will be the remaining factors of the integrand. Note that dv always includes the dx of the original integrand. So that's the book's suggestion. If you don't find that helpful, I have a mnemonic device that I use here on the next page. I call this LibT. And LibT is just an acronym, and I use it as a mnemonic device where the L stands for logarithm, the I stands for inverse trig function, P is for polynomials, but I use the term loosely. It's any expression involving powers of x, and that includes constants. A constant has a power of x that is 0. And then the t is trigonometric functions, and the e is exponential functions. So it is a device for selecting u. And notice I put here whichever type of function in our problem is closest to the top of the list is our choice for u. So down below there's an example. Consider the integral x times sine of x. Well, if x is a polynomial function, that would belong to the letter p, and sine is a trig function, that would belong to the letter t. Which one is closest to the top of the list? And we would say, well, the p is closer to the top of the list than t, so we're going to say let u be x, and let dv be sine of x dx. So according to LibT, let u be x and let dv be sine x dx. That is an easier way for us to make our choices. I didn't think that the textbook guidelines here were all that helpful. So we have this little device. Every time you have an integration by parts problem, you will write LibT on the side and use it to choose your u. And once you choose your u, everything else is your dv. And as the guidelines said, the dx has to be part of your dv. Now, the next thing is, when do we use integration by parts? And the best example or the best explanation is when you have two dissimilar functions, x and sine of x and e to the x, log of x and sine of x. It's not 100% guaranteed to be dissimilar functions. Sometimes you can use it with functions multiplying themselves, such as sine squared x, secant cubed x. Those functions will work as well. But often a good rule of thumb is if you have two dissimilar functions multiplying each other, integration by parts is likely your candidate for finding the antiderivative. So here's our first example. We see that we have x times e to the x. Two dissimilar functions, integration by parts should come to mind, but then we say, well, let's write our acronym, libT, and use it to choose our u. So we see that we have an x that belongs to the polynomials, and we see that we have an e to the x that belongs to the exponentials. So the closer we are to the beginning of the word is going to be our choice for u. That means that u should be equal to the polynomial term, which is x. So we're going to say u is equal to x, dv is equal to e to the x dx. And now to finish this, we need to use the integration by parts formula. So the integration by parts formula says the integral of u dv is equal to u times v minus the integral of v du. Remember, we got this formula by reversing the product rule derivative. And now we say, well, I have u, I have dv, but I don't have du, and I don't have v. Well, we can find those components from what we have here so far. So since u is x, we should be able to find du. So the derivative of x is going to be 1 dx. And we know that dv is e to the x dx, so the antiderivative would give us v. What's the antiderivative of e to the x dx? It's e to the x. And now we can plug all of these components into the formula. U dv would give me x e to the x dx, that's the original problem, equals u times v. So let's write our solution, equals u times v, so it's x e to the x, minus the antiderivative of v, which is e to the x, du, which is dx. And we say, well, we just did this antiderivative. We know it. The antiderivative of e to the x dx is e to the x. So now we can write the next phase of our answer, x e to the x minus e to the x. And since it's an indefinite integral, we have to add our constant of integration. And this is our answer. And now that we have our answer, we say, well, how can we check this answer? How can we check to be sure it's correct? And because derivatives and antiderivatives are inverse operations, if we take the derivative of this answer, we should get back the problem we started with, which was x e to the x dx. I will leave that as an exercise for you to do so you can verify that this is indeed the correct answer. So here's our next example. Again, we want to start by using our mnemonic device, libT. And we say, well, we have a logarithm here, so that's going to be the very front of the acronym. And then we have x squared, that's a polynomial, that's the p. So we should know what our choices are. U is whatever's closest to the front of the word, so natural log of x. And then dv is everything else that's left, including the dx, so it's x squared dx. And then from there, we want to recall our formula for integration by parts. The integral of u dv is equal to u times v minus the integral of v du. We know u, now we have to find du. If u is log of x, then the derivative is 1 over x dx. And if dv is x squared dx, then v is its antiderivative, which is 1/3 x cubed. Now that we have all of these components here, we want to take them and plug them into the formula. So u times v gives us 1/3 x cubed times natural log of x. Subtract the antiderivative of v du, which is 1/3 x cubed times 1 over x dx. We can simplify this algebraically. So now we get 1/3 x cubed times ln of x minus, I'm going to pull the 1/3 out front, the antiderivative, the x cubed and the x cancel to give us an x squared dx. By power rule, we see we get a 1/3 x cubed times this 1/3, we'll have a 1/9 x cubed. And then, as always, our plus c is our constant of integration. And to check this, you would use the derivative to find the answer. See here, you would need the product rule for derivatives, and this is just a power rule. And it should all combine and simplify back to the original problem. Okay, so in this example, we see that we only have a single function. That function is arc sine of x. I put a little comment here. The comment says that when we are working with a single function and we would like to use integration by parts, we can introduce 1 as that other function. So if we look at this integral, we can say that we have the definite integral from 0 to 1 of 1 times arc sine of x and in doing this, we would identify the 1 as our polynomial. I said earlier that constants are polynomials with the exponent of 0 on their variable, and the arc sine is our inverse trig function. And we say, well, if this is the I and if this is the P, and we're looking at lip T, then we want the letter closest to the beginning of the word to be our U. So we see that I is closer than P, so we're going to let U equal sine of x. I'm sorry, arc sine of x. Let's fix that. And we're going to let dv equal 1 dx. Remember, the dx always attaches to the dv. Now we know we need the counterparts, the du and the v, for our integration by parts formula. So the derivative of arc sine of x is 1 over the square root of 1 minus x squared. And v is equal to x. Oh, I can't forget to put my dx here with the du. It's the derivative. So we go back to our integration by parts formula. We know it's going to be equal to u times v minus the integral of v du. We want to plug each of these components into the formula. So u times v is x times arc sine of x minus the integral. V times du gives me x over the square root of 1 minus x squared. And then my dx. And here we should recognize that we can use u substitution. This is a different u variable now from the integration by parts. So if u is equal to 1 minus x squared, then du is going to be equal to negative 2x dx. And we say we have to adjust that. We're going to put a negative 2 out in front here, and then we're going to balance it with a negative 1/2, but that double negative makes this a positive. And now we see we have x times arc sine of x plus 1/2 times the integral. So if we look at this integral, Everything on top here gets replaced by u. Everything down here is, everything on top replaced by du. Everything in the denominator replaced by u. So it's 1 over the square root of u, which is u to the half power, u to the negative half power du. And when we evaluate that, we add 1, we have u to the half, divided by half gives me 2u to the half. So I'll put that in here. So we have x times arc sine of x. And now we have plus. We see that the 1/2 and the 2 cancel. I'm going to replace u with what we say was equal to 1 minus x squared. We see u has a half power. I don't need my plus c because this is a definite integral, so I'll put my vertical bar with my bounds of integration. And now we can evaluate So when we plug in a 1 here, we have 1 times arc sine of 1. Arc sine of 1 is pi over 2. Plus, when we plug in a 1 here, we have 1 minus 1 squared is 0. So that is with our upper bound. Now we have to plug in our lower bound. When we plug in 0, 0 times arc sine of 0, well, arc sine of 0 is 0. So 0 times 0 plus 1 minus 0 is 1. The square root of 1 is 1. So we have 0 plus 1. And our final answer here is pi over 2 minus 1. If you want the approximate decimal answer, that is about 0.571. And that's an example where you have a single function, but we use integration by parts. And in doing so, we used 1 as our second function. And we went through the lib t to choose what is our u and v and dv in our formula. We plugged everything into our formula, and we found that u substitution was embedded in this problem. And then we had a definite integral, so we plugged in the bounds and evaluated it. And this is the exact answer and the approximate answer. Okay, so in this example, we see that we have a polynomial, x squared, and we have a trigonometric function, sine of x. And if we go to our mnemonic device, we see that p comes before t, so our u is going to be x squared. So we can set up our substitution here. So u is x squared, dv is sine x dx. And then we want to find the counterparts. So we want to find du, which is 2x dx. And we want to find v, which is the antiderivative of sine of x. So we get negative cosine of x. And then, of course, there is the integration by parts formula. The integral of u dv is equal to u times v minus the integral of v du. And the u dv is the x squared sine x. That's the given problem, so we're interested in the right-hand part of this formula. So u times v gives us negative x squared cosine of x. minus the integral of v du, so that's a negative 2x cosine of x, and dx. So we see we went from a x squared with a sine x to a linear x with a cosine x. So we need integration by parts here again. And we should see a pattern that if we have a power to x, that power is going to tell us how many times we're going to have to use integration by parts. After one iteration, we went down from a square to a first degree, and after the next iteration, we'll go from a first degree to 0 degree, and we should be able to integrate. So we're going to do this a second time, and I'm going to use a subscript now. I'm going to say this is my p again, and this is my t. So we see that the polynomial part will be our u. I'm going to call it u with a subscript of 2. And our dv with a subscript of 2 is cosine of x dx. Now our derivative of u, subscript of 2, is negative 2 dx. And our v, with a subscript of 2, is the antiderivative of cosine, which is sine of x. And now we want to plug all of this into the next integral. So I started writing the negative x squared cosine of x minus, and now I have a big bracket here because this integral is going to be replaced with u times v minus the integral of v du. So this integral is going to be substituted by the integration by parts result. So u times v gives me negative 2x sine of x. Minus the antiderivative, and now we want v du, so it's negative 2 times sine of x. And then our dx. And we can close our bracket. So all of this was replaced by the integration by parts formula, and we have to distribute our negative through here. So we're going to get negative x squared cosine x. And now this double negative makes this a plus 2x sine of x. And when we distribute this negative again, that makes this a plus. But I'm going to bring this negative out and bring it back to a minus. I'm going to bring the 2 out also. And the antiderivative of sine of x is negative cosine of x, and then plus c. So this double negative makes it a plus 2 cosine x plus c. So we see that we needed to use 2 iterations of integration by parts. And the number of iterations that we would need to do is related to the power that we have on our x variable. And if we come back up to look at that again, we can keep taking derivatives of x squared. So it went from x squared to 2x, then the derivative went from 2x to 2. So we have to keep taking derivatives until we get down to a constant. Sine is something that we call an infinitely integrable function. So we can keep taking the antiderivatives of this until we get our du to come down to a constant. So whenever we have a polynomial to a power that is going to count down to a constant times a function that has infinite integrals, we can use this repeated use of integration by parts. And sine x is one of those infinitely integrable functions. Cosine x is an infinitely integrable function, and so is e to the x. So if we have a power of x paired up with sine, cosine, or e to the x, we would use this process. And the exponent on x tells us how many times we would have to use this process. So in this example, we're going to use the tabular method to complete this integration by parts problem more rapidly. We see the x to the fourth tells us that we would need to do 4 iterations of integration by parts. We don't want to do integration by parts 4 times. This is a problem that can be done in a very rapid way. It's called the tabular method. So first thing we're going to do is set up our table. The first column will handle the sign of the expression. We always start with a positive, and then we alternate to negative, positive, negative each term. And then the next column is going to be the u column. And we see from this example that our u is x to the fourth. We determine that using the Lipti algorithm. And then our dv is going to be cosine of x. And then the next row will be a minus. And with the u's, we usually find du's, the derivative. So u, du. So we want the derivative of x to the fourth, and that will give us 4x to the third. And with the dv's, we find v. That means the antiderivative. So the antiderivative of cosine of x is sine of x. And then we'll go to our next row. The signs are going to alternate. Now we have a plus. The derivative of 4x cubed is 12x squared. The antiderivative of sine of x is negative cosine of x. And then we're ready for our next row. Change the sign again. Take the derivative again. Take the antiderivative again. And we keep doing this until our u column generates a 0. Then we stop. So once we got our 0, we stop. And now we're going to use this table to generate each term of the antiderivative. So the way this works is we take the sine with the u, and then we group it with the v. We say, great, now let's take the next sine with the next u and the next v. And we keep doing this. And these will be each of the terms of our answer. And we multiply each of these components together. Now here, anything times 0 is 0. There's no need to go on anymore. And now we can see our first term to our answer is going to be a positive x to the fourth times sine of x. So let's write our answer here. Equals x to the fourth times sine of x. And then our next term is a negative 4x cubed times a negative cosine of x. Well, a negative times a negative is a positive. So we have plus 4x cubed cosine of x. And now we have a positive 12x squared times a negative sine of x. A positive times a negative gives us a negative. And then a negative 24x times cosine of x. And then a positive 24 times sine of x. And because this is an indefinite integral, we need our constant of integration plus c. And that's our answer. Okay, so in this example, we're integrating secant cubed of x. And because we don't have any different functions, they're all secant x functions, lib-t doesn't really help us out. So the way we start is we split up the function and we say, well, if we split up this function, there's not really many options that we have here. Basically, we're going to write it as secant squared times secant. And we go back to the original textbook guidelines, and the guidelines say, which of these would you rather integrate, and which of these would you rather take the derivative of? And we say, well, we know how to integrate secant squared, and we know how to take the derivative of secant x. So if I want to integrate this, it should be my dv. If I want to take the derivative of this, it should be my u. So we say let u equal secant x and dv equals secant squared x dx. Then when I take the derivative here, I have du equals secant x tangent x. And a dx because it's a derivative. And my v is tangent x. So because I know the behavior of this function, I'm going to write out the entire integration by parts formula, including the original problem, and that's going to help illustrate something that's going to occur here. This is one of those special problems where we're going to use a couple of different techniques. So here's the original question, and then we're going to say, well, now we need to follow with uv, so it's secant x times tangent x. Minus the integral of v times du, so it's going to be secant times tangent squared x dx. And the part that we need to introduce here is, if I rewrite this using a Pythagorean identity, I can convert these all back to secant x. So we're going to replace tangent with secant squared x minus 1. That's the Pythagorean identity equivalent. And when we distribute the secant x through here, we're going to get secant cubed minus secant x. So I'm going to write the whole thing out again. And I'm doing this to help show what we need to catch with this type of a problem. So I'm taking minus the integral of secant x times secant squared. That's going to give me minus secant cubed x dx. And then when I take this minus integral of secant x and distribute it to the minus 1, it becomes a plus. The integral of secant x dx. So we distribute it through here, and we have two separate integrals. Now, the thing we want to point out is that if I add this to both sides of the equation, then I have eliminated this extra secant cubed term. So these two will cancel each other out. And then these two will combine and give me 2 secant cubed x. 2 times the integral of secant cubed x dx equals secant x tan x and this is gone, so now we need the antiderivative of secant x. We should have that memorized as the natural log of secant x plus tan x, so that's what we're going to put down here. And then a plus c. And the final step is we don't want to know what 2 times the integral of secant cubed x is. We want to know what 1 times the integral of secant cubed x is. So we divide everything by 2. We don't want to know what 2 times the integral of secant cubed x is. The question asks us what 1 times the integral of secant cubed x is. So we need to divide everything by 2. And we see that these 2's here are going to cancel. And then we have 1 times the integral of secant cubed x dx. And it's equal to secant x tan x plus the natural log of secant x plus tan x all over 2 plus c. I didn't divide the c by 2 because an unknown constant divided by 2 is still an unknown constant. So this would be the final answer here. The techniques and strategies were combining like terms, using Pythagorean identities. This is something that we'll see more in the next section, dealing with powers of trig functions. And this exact example will be referred back to from this section as to how to handle secant cubed. But if we didn't write out the full secant cubed x dx, we might have found that we were going in circles, and we would have seen this popping up again. And we say, well, let's just combine like terms. So this strategy of combining like terms allowed us to eliminate going through a circular motion with finding the answer. And we just took care of it through simple division. And that is the end of section 8.2.